So continuing in our discussion about regression, let's go into the idea of multiple linear regression. So in multiple linear regression, we have the least squares estimation of parameters. We have macro and micro significance tests. We have standardized regression coefficients, goodness of fit statistics. What's new for multiple linear regression versus simple linear regression is that we now have the adjusted R-squared that we're looking at. We also need to be concerned about multicollinearity detection. If our VIF values are greater than 10, we definitely have a problem. And then we also want to look at some cautions with multiple linear regression. So going back to our multiple linear regression, similar to what you've seen before, you have y hat equals alpha plus beta x, but now we have x2 and so forth to represent however many variables we have in our model. Remember that alpha and beta are parameters for our population values. Our intercept plus k parameters. This is why we have a total of k plus 1 parameters when we're looking at our models. When you think about multiple linear regression, it's not a flat line. So now that we have two predictor variables, we start making a plane of our data. And so we can see the plane of our data, or maybe even a contour plot in what we see here on the right-hand side. When you look at the output, your coefficients for the variables are included in the least squared solutions. These are closed solutions given by our matrices formulas that I'm not really going to make you worry about. But when you see that solution down here at the bottom, these coefficients are the values that you typically see in your regression models. When we do a test of significance, really what we're looking at is, we're looking at these beta values being equal or not equal. So if at least one of our beta values not being equal to 0 would give us a significant f-test. Remember, this test is, of course, limited in identifying the significance in terms of the model. All it tells us is if one of my relationships is different. But the way we get this value is you're going to do your sum of squares residual divided by regression divided by k, which is your number of parameters in your model. We have sum of squares residual divided by n minus k minus 1. Or we can just do our mean squares regression divided by our mean squares residual to get our f statistic value. When we keep working with that standard ANOVA, here are some more calculations of how we can get the sum of squares regression and sum of squares residual, as well as our sum of squares total. But the whole purpose of doing all these sum of squares calculations is to ultimately get your F statistic. Because what you're doing is you're going to be looking at your F statistic in comparison to the F statistic on the F distribution table to see if your null hypothesis is, if you reject the null or if you fail to reject the null. Remember, if you fail to reject the null, that means that none of the values are statistically significantly different from 0, and you really don't need to look at anything else in that model. You might want to consider taking some variables out so that you can make an overall statistically significant model. We use what we call the partial F statistic to look at your models being nested, when your models are nested. And it allows for you to compare two hypotheses. So you're looking at your reduced model and your full model for whether or not your beta values are different from 0. A significant partial F statistic is going to tell us that the variables in the larger model are going to contribute significantly to the prediction in the response variable. Conversely, our partial F statistics are used to indicate which variables we can also exclude from our model. We also look at R-squared and adjusted R-squared. With multiple linear regression, you do need to report both of them. R-squared is calculated the same way for simple linear regression. Adjusted R-squared, basically, if you notice here, we're taking our R-squared value and we're dividing by n minus k minus 1. So the more parameters that I have in my model, this is going to bring my adjusted R-squared down. And so this value is being used to account for the complexity of the regression in the model, allowing for models of different sizes to be able to be compared. So if we did an example with adjusted R-squared, let's say our sum of squares total was 245. We had 15 observations. Our sum of squared residual was 90. And so the way we can find our adjusted R-squared is we plug the values into the equation from the previous slide to get an adjusted R-squared value of 0.53. But if we suppose we have an additional value, and that changed our sum of squares residual to 88, that's now going to bring my adjusted R-squared down from 0.53 to 0.49. For the same data set, we just now have an additional predictor variable in my model. Our hypothesis test that we're doing with our t-test when we're looking at the individual coefficients in our model, we're looking at whether or not our t-tests are statistically significant from 0. And so when we look at these t-tests in that parameters estimates table, we're looking at the partial or marginal test. And what that means is saying, if I have other beta values, do I really need this one? When we're looking at our standardized regression coefficients, it's often difficult to directly compare regression coefficients due to having a variety of dimensions or scales of our data, right? So you might have a predictor variable of salary, which goes anywhere from 0 to 6 figures, and then you might also be looking at hours worked during a week, which should only go up to about double digits, right? So the betas allow for this discrepancy in the scales of your data to be compared. So therefore, the relative importance of your variables are not being analyzed directly when you compare these coefficients. And so, so standardizing your regression kind of takes that dimension out. Sometimes you use unit normal scaling. Basically what that means is that's going to scale the points that are being used in your data set. Often we use our standardized coefficients to assess the relative importance of our variables. If we have standardized regression coefficients and any of our regression equations are measured on the same scale, and so we have a mean of 0 and a standard deviation of 1. And then we can directly compare them to each other, looking at our largest coefficient indicating which independent variable has that greatest influence on our dependent variable. In prediction, make sure you're being very careful about extrapolating beyond the region that contains the original observations, because as we go to the edges of our predicted model based off of our training data, our predictions become less reliable. Some things, we're going to look at hidden extrapolation in multiple regression still. And so we're going to define that smallest convex set containing all the original in data points as a regressor variable null, RVH. And if at any point one of our points lies inside or on the boundary of this, then the prediction or estimation is going to involve a certain amount of interpretation. Well, if the point's outside of this, extrapolation is something that we're going to have to do. We're going to have to kind of figure out what the relationship is outside those bounds. Multicollinearity is one of the really serious problems with multiple linear regressions, because we want to make sure that the variance that is explained in our y variable from an x variable is not also explained by another x variable, because then we have that overlap of explanation in our variables. And so this can end up becoming a very serious relationship. Multicollinearity is going to imply that we have a near linear relationship between the two different x variables. And so that gives us something that we need to look at when we're looking at our data sets. Because the presence of multicollinearity can dramatically impact our ability to estimate and predict new values. So when we're looking at multicollinearity, here we have our data set that where there's multicollinearity, and we see that all the data points kind of are parallel to one another. But when we have orthogonal regressors, we see that they all intersect each other. And so this is going to be important to that multicollinearity diagnostic that we look at. We can calculate the variance inflation factor by taking 1 over r squared sub j, where that's the coefficient of multiple determination obtained by regressing x sub j on our other regressor variables. Our r squared value has to be between 0 and 1. So that gives us a VIF value being anywhere from 1 to infinity. Anything over 10 means that we absolutely have multicollinearity. Recommendations tend to be to keep those VIF values between 1 and 3. 4 is kind of okay. But basically, if your X predictor variable is highly correlated with another X predictor variable, then your R squared is going to be inflated and larger than it needs to be. So if we're looking at our tree examples, we might find evidence of multicollinearity by looking at the correlation matrix that gives the correlations between variables. So if we see anything that has a collinearity or a correlation value of 0.75 or greater, that's going to indicate that we have high multicollinearity. So here you see bark thickness and height, and diameter at breast height and height. So I expect to see high multicollinearity between these two variables and height. So when we're talking about multicollinearity, this is looking at variables that are basically measuring the same thing. Okay, so if I look at the relationship, if I look at the model where I just have diameter at breast height versus the model of bark thickness, you see that, our significance values are about the same. Our t-tests aren't that much different. And we see some different variables for our slope values, but that also makes sense due to the scale of the predictor variables that we have. One indication of multicollinearity is that when we have the variables listed as separate in the models, like we have in the first two models, and then when we put the two variables together within the same model, we see that the coefficients are changing drastically. This is indicating that there's a certain amount of interaction between the two variables that we've added into the model. And so you can look at the correlation matrix between those variables to figure out if we have any potential problems. You can also look at factor analysis. If you look at tolerance and VIF values, this is going to be a measure of the degree that the independent variable is explained by the other independent variables. And so when we're looking at a VIF value where 1 over tolerance value is greater than 5, that's going to indicate that collinearity should be investigated, and anything over 10 should definitely be looked at, because that's telling us that it may not be overlapping with just one more variable, it could be overlapping with several variables. So some things that you can do if you have multicollinearity in your data is you can always collect more data. You can collapse variables by combining them together or eliminating models from the model completely. When you're looking at the number of variables and observations that you want, generally if you have one dependent variable and one independent variable, you want to have a minimum of 30 observations. And then in general, when you add more predictor variables or independent variables, you want to add an additional 10 observations for each additional independent variable that you add. The number of independent variables in the equation really kind of get limited by two things. They should be included in the equation if they're based on well-defined model about the factors influence, to look at their influence on the dependent variable, or variables that don't contribute substantially to explaining the variance in the dependent variables should be considered for evaluation elimination from your model. After the main effects of your model have been determined, then additional interaction terms can be investigated. So x1 times x2 or x1 squared or whatnot. Some cautions with multiple linear regression is it doesn't explain the relationship between our independent variables and our dependent variables if those relationships are not linear. So we really have to make sure that we have linear relationships to be able to use this modeling to tell us something about our data. OLS, multiple linear regression, or ordinary least squares, is typically used to predict dependent variables measured on interval or ratio level. If our dependent variable is not measured at interval or ratio level, then we have to use other techniques such as logistic regression to predict those outcome variables. Some more cautions. OLS assumes that the independent variables are measured at interval or ratio level. If not, we end up with a lot of prediction error. When we have nominal level variables used, we need to use our dummy variables. And ordinal coefficients may indicate our ranks. So 1 could be staff, 2 supervisor, 3 manager. So when we interpret the coefficients, it becomes really problematic if we use that interval scale without it being a ratio scale. So oftentimes if you have ordinal scale like that, it might make more sense to turn those into dummy variables or find a different way to code that data. So going back to our Redwood data, if we're applying our model, remember we have our appropriate predictor variables here, but let's say we add a new case or a new independent variable with our values, so we can make our prediction model a little bit longer. So here we're looking at our Redwood data again, and we see that our diameter at breast height and our bark thickness are both included, which allows for our final equation being our height equals 66.869 plus 2.068 times 33, because we want to know about a tree with a 33-inch diameter, plus 13.861 times 3 from our bark thickness, to get a predicted height value of 176.696. So, how come sometimes our regression coefficients end up with the wrong sign? Sometimes the regression is too small. The range for it isn't big enough. Sometimes we don't have our important regressors included in our model, or we have multicollinearity within our data or within our predictor variables. And sometimes we've made just simple computational errors in the preparation of our data.